as was rightly stated, I now work for Velux on the commercial side with Atria and large commercial installations of skylights. But I was asked to do a presentation on not necessarily the future of smart glazing, but a slightly more traditional method of how to control daylight coming into a space. So, start with a quote there, 1925. If anything, that's more important now than it was then, with the huge glass facades that we see coming into buildings. It's now more of a struggle with light than for light. So we'll start with something a little bit more holistic, that if you take a moment to think about a space personal to you where you feel rejuvenated, refreshed, where you feel stimulated, whilst at the same time being fairly relaxed. Very few of you, if you think about it, will come up with the office that you work in. Research has shown that over 60% of occupants of commercial space feel that they have anything like enough access to daylight throughout their working day. And when you consider that in the Western world, we spend roughly 90% of our time indoors rather than outdoors, having no access to that natural light has a huge impact on our well-being and our circadian rhythm to kickstart our day, to finish the day. So we try and think about, as designers, as builders, as occupants and building owners, what do we need to do? What do we do to bring that access to daylight, to give us that access to the environment, to view? How do we make the most of what's available to us whilst minimising the cost attached to it? And the answer's always been there, that we've got the big ball of energy available to us all the time. So it's free, it gives us warmth, it gives us light, but unobstructed it gives us problems, it gives us issues that we have to think about how to overcome. So unobstructed, there's roughly 100,000 lux coming into a building space without any sort of tint on the glass or any sort of shading. That obviously gives us two issues, one being glare and the other being heat. So we know that we need to design around that. And the more research that comes in, the more legislation that comes in, the more we want to make use of that natural light, that natural resource to us. But we do have to control it. And we've spoken, or Ruth spoke about various methods of shading before the invention of dynamic glass. Physics will dictate that stopping the sun external to the space is more effective than internally. But we also know that that can have aesthetic issues with the design of a building when you have brise-soleil slapped all over the building, any sort of movable roller shade or external Venetian blinds that you see more in the continent than the UK. They're expensive, they're hard to maintain, and they have their issues as well with how they control that light coming in. So what I'm here to talk about predominantly is flat fabric roller shades that are internal. So you do get a heat build up between the shade cloth and the glass, but in most commercial environments now where you've got it built up into a pocket, that can be installed in such a way that you have a punch system that allows that heat build up between the glazing and the shade cloth to go up into the ceiling void and be dealt with by the return air system. So it's a compromise. Everything's a compromise on what you're looking to achieve, whether it's pure building performance, the energy and utility cost of running the building, or whether you're looking for the best occupant comfort that you can achieve. And there's a line there, and you have to decide on who the occupants are as to where you want to position your building. So to go through, before we go into the wondrous world of automating your shading, just a couple of quick points that need to be considered. Guthries, you'll be looking at things like this with your trapezoidal, weird, enormous shapes. But two key elements that you need to look at is the openness of the fabric. One of the points Ruth made is that when you have a shade of any sort, it restricts your view. With technical fabrics now, you can bring down a very low openness to the weave and still maintain a view through the shade cloth to the environment outside. So in the UK, we would recommend on the southern facade of a building you need something like a 3% open fabric. The problem you have is if it's not a technical fabric, then you find light transmits through the core of the fibres of the fabric itself. So it may say it's 3% open, but you may have a visible light transmittance of 35 to 40%. So by using a high technical fabric, that 3% gives you around about an 8 to 9% visible light transmittance through the fabric. The denser the fabric, the less your view. The more open the fabric, the more glare is allowed through and the more radiant heat is allowed through. And the other key element is colour. Most people, when you talk to them about what colour they want for an internal shade, they would go as light as they possibly could, thinking that you can maintain a view through a light fabric. And it's actually the opposite is true. When you've got a very light cream to a white fabric, the sun behind it tends to make it glow like a light bulb and actually restricts your vision through the fabric. And like for like, these are exactly the same fabrics, technically speaking. Through a darker fabric, it mats that effect of the sun and allows you to have a much clearer view through the fabric. There is a play-off to that a darker fabric absorbs and re-radiates heat a little bit more than a light cloth, but once the sun's inside the building, that effect is actually quite minimal. It would have a bigger effect outside. So if you're looking at the design of what you're looking to achieve within the building, everyone, not an architect who hasn't got a tagline of sustainability somewhere on the front page of their website. So there's two key things: environmentally designed factors, the material health of the fabric, the system, whether it's recyclable, whether it's been recycled in the first place, and then the system that you install, whether that can offer genuine energy savings for the building itself. And then the other factors are the human factors. What your shading system can do for the health of the occupants, and they're the obvious ones of their thermal and visual comfort within the space. So we'll have a quick look at the health side of things. I'm sure you've all come across various studies to do with our response to daylight. The human response is critical to have access to natural light. Now, you don't need too much. It's advised that once you've eaten that you go for a walk or go outside your building for 15 minutes. That would all it would take for you to digest your food better and be able to settle into the afternoon and carry on working, rather than having that dip in your metabolism that makes you slow down between sort of 2 and 3 o'clock in the afternoon. Previous to all of this sort of research, lighting companies researched that dip, and their answer was to ramp the artificial lighting up to 120% to try and force focus back into people during that time that they have a dip. But you also have all sorts of other responses to light. It's not just kick-starting the circadian rhythm in the morning with the yellow light from the sun. It helps to regulate your cardiovascular system. It reduces the impact of asthma, emphysema. There's even links to reductions in the risk of breast cancer with access to good natural light. And a key thing is sleep. If you've had a day where you've had more access to natural light, you are sleeping on average 45 minutes a day more than people who have no access to natural light. So over a week, there's more than 5 hours of extra sleep you get a night, which obviously helps with your concentration, your focus, and your productivity. There's also studies that we'll go into a little bit where educationally children can focus for longer and absorb more information if they have well-ventilated and naturally lit space. There was 21,000 students across America that were monitored, and the difference between the best and the worst day-lit rooms was 26% in the results of both English and maths. So it's astonishing the impact that access to light can have on education. On average, people in recovery in hospitals, if they are sat on the perimeter of the building with access to natural light, they recover 7 to 8% quicker than people that are in the core of the building that don't have that access to the environment. So that has cost implications, that has savings for building owners. And then you've also got regulation. Better design better energy absorption or energy use of a building, gives you higher LEED, higher BREEAM points, whether you're talking about the Living Building Challenge, the Well Building Standard, whether it's more local ones. America have codes for every state, wherever you go, they're all different. But that gives you higher rentable space, let alone all the other bits that it does for the human beings within inside it. So daylighting or lighting strategies have been around for a long time. Daylighting strategies have been incorporated into that over the last few years, but most buildings aren't achieving it. And this goes back to the 60% of people feeling that they don't have access to enough daylight. This is a building that achieved LEED status based on the design for light and natural light coming in, but there's something very wrong with the picture. You've got a lovely blue sky, yet the artificial lighting is ramped up to 100%. And that's because they got the points allocated for having a shading system, but it was manually controlled. So Ruth pointed it out earlier, and I'll probably point it out 4 or 5 times. When you have a manual controlled system, you defeat the object of having a shading system in the first place. Almost everybody, the windows in Ruth's study were in the southeast corner, or facing southeast. If you were sat in your office first thing in the morning, you would get that sun streaming through your window in an office. So you get up almost every time, because it's causing a glare problem bouncing off your screen or bouncing across your desk. You will get up and manually pull that shade down, but the very clever artificial lighting system will respond to that, ramp the lighting up to 400 or 500 lux in your working plane. You forget that you've pulled the shade down at all, and because that artificial light is maintained through the day, you're getting on with the job in hand of actually just working for a living. So again, as Ruth said, unless you are connected to daylight yourself, you're very unlikely to get up and open that shade again. So the light is burning all day long to compensate for a sun that moved around several hours ago. So we move on to how to actually give that an actual response to the building so that you can start getting some payback. So by having a proper window management and automated response, then you can start managing not just internal shades, but there is even research going on and collaborations going on at the moment that automated systems can start driving smart glazing systems as well and start helping interpret the information. But they can automate exterior louvers, brise soleil, exterior roller shades. But there's several versions of how to do it. You can have simple timed devices, which you'd see in your home. You know, you can, when you go on holiday, you used to plug a little device in so your lamp came on at 7 o'clock in the evening and went off at 7 o'clock in the morning. There's slightly more advanced versions of that available. You then have sensor-driven, where you have sensors all around the perimeter of the building looking for light levels. And then you have science-driven technological systems that are driven by real-time data. These systems, scientific systems, give you, on the one side, energy savings, physical utility cost savings in the building, but also help protect the occupants from thermal and visual discomfort. This is an example, this is a New York Times building, but it's an example of an incredibly well thought out daylighting system. The shades never drop below the working plane because glare never comes up underneath that unless it's bouncing off a lake or something. So you never need to drop the shades to floor level with a floor to ceiling glass. That's also allowing natural light to flood into the stairwell where there's not anyone sat there at any given moment. It's just a passing through area where higher levels of light actually help you to stimulate your brain. But you also have shading responding. You have very little artificial light operating for large chunks of the day. And it's not just for new builds, it's not just for advanced thinking of buildings like the Shard. This is a building, a warehouse from 1930 that achieved LEED silver status through renovating and automating the solar response and having the lighting system upgraded along with other systems with the air conditioning. So it is adaptable. It's scalable and it's adaptable, depending on what you're looking to achieve. It's all backed up by case studies that are not they're not driven by the manufacturer. New York Times has been studied for 6, 7 years, 8 years now by the Lawrence Berkeley Laboratories, University of California. We'll move on to that one in a minute. But there's been huge studies with Perkins and Will. There's been the Genentech building, the highest standards of office utility cost in the US. Genentech exceeds it by 29%. It's an astonishingly well thought out building. So the New York Times, because of the automated shading system that was implemented, 43% of the energy that would have driven the artificial lighting was saved. The payoff of having, or the compromise of having an internal shade of driving heat gains up a little bit. Even with that taken into account, 24% of the total utility cost of running the building was saved because of allowing so much natural light into the space. It was unusual in New York. It was ultra low E, very clear glass. Up to the time this was implemented, you normally saw a tint in the glass in Manhattan. And that equated to $600,000 a year in utility cost of operating the lighting system. I can't give you the actual cost of installing it, but what we can say is that less than 5.5 years to pay back the total installation, not the automated elements of it, but the entire installation, including the core shades. We will expand on this in a minute, but in the first year of installation, less than 5% of all operations of the blinds, bearing in mind they moved in 5 increments up and down the window, depending on where the sun was, less than 5% of all operations were manually driven. So they had control panels throughout every floor plate, and anyone could get up at any moment and drive the shades up or drive the shades down as they saw fit. And they had to choose why they were doing it: too hot, too bright, too dark. Most of the time, nearly 3%, they were driving the shade more open, saying that the installation was being a bit conservative on the amount of light they were allowing. Only less than 1.5% were driving the shades down because of a glare problem. We did a post-occupancy review of who was driving the shades up and down, and there was one gentleman that did it every single morning. He came in, sat at his desk, drove the shade down, left it there all day. So they went and spoke to him why, and he was basically paranoid that the building opposite could see him typing all his passwords into his computer in the morning. So he came in and just drove the shade down for privacy. So they couldn't talk him out of it, so they took that blind out of the automated system entirely and just left it permanently down. You can't, again, Ruth mentioned this, you can't overcome people's need to want to have some sort of control themselves, however automated the system is. As I said earlier, that you can have sensor-driven or scientifically driven solutions to automation. And the real difference is what it's measuring, what it's looking at. Most sensor-driven, they're just photocells. They're looking at visible light. And that's less than 50% of the spectrum of solar radiation. When you have a scientific, a technology-based system, you have what's called a radiometer, which looks like that. That is about that big. That's all you need. One of those sat on top of the very highest point of the building, so no part of the building is creating a shadow, otherwise it thinks it's cloudy. And it looks at 180 degrees, it looks all around, but it looks into infrared and into ultraviolet, and it gives you a much more comprehensive picture of what the prevailing microclimatic conditions are, not just visible light. So it allows you to start mapping not just whether it's sunny and whether it's cloudy, but whether it's bright, whether it's overcast, whether the conditions are changeable. And if you're sat there, David will recognise this probably if you're from Glasgow, isn't it? When we start looking at what we need to do to respond to what is a very dynamic thing. The sun is constantly moving in its azimuth, its altitude, so the profile angle of the sun hitting a building changes constantly. So if you have a fixed solution like a brise-soleil or a non-moving brise-soleil, that can only give you a worthwhile response at certain times of the day or certain times of the year. So by having a fully automated system, you can work around, you can plan. The sun's predictable. Although it's constantly moving, we can predict exactly where it's going to be in relation to any building, anywhere in the world, of any geometry, any orientation. So you can dictate that on any elevation, the use of the space can be very different. You may have in one room people working right up to the window wall, right up to the curtain wall on desks. The next room is a breakout open space. So the allowable light coming into that space could be very different. This sort of system allows you to map each and every room in the building and dictate exactly how much sun you can allow into the space. So you can draw a line in the floor in every room saying sun never crosses 3 meters, because that's where the space would start to reflect up into people's face, whereas the next room down to 1 meter. And this will allow you to program the system, and effectively it presumes it's a beautiful clear sunny day like today, all day every day. And because the sun's position is predictable, it will put the shades wherever they need to be to stop the sun crossing that line. This little fella, it basically sits in a hierarchy. It sits above that pre-programmed solution and looks at what's actually happening out in the sky. So if it's cloudy, it can override the system and say, actually, all the shades in the whole building can open up, stream the daylight in, because there isn't a glare problem, there isn't a heat problem coming from the sun. But as we know, this could happen anywhere. You've got fairly dark cloud on the left there, you've got bright cloud, and this is a bit you'll see in Glasgow a lot, or Aberdeen. You've got clear sky, which you might not see quite so often. You've got shadow falling on the building, and you've got direct sun hitting parts of the building as well. So how do you respond to all of these different elements at the same time? So you can add on several things. We've already got the hierarchy there that says actually the sun is being covered by cloud, so we can drive all the shades up. But we can build in a comfort line as well, so that anyone in the space that says actually the shades are reacting too quickly or too slowly to either the sun coming out or the sun going away, that line can be moved so that even post-occupancy, the whole response of the shading in the building can alter, whether it's a change of owners or just people wanting to alter the response. But as I was talking about, you can dictate how much allowable sun, solar penetration comes into any given space, and it will never pass beyond that line, so you're never going to get it bouncing off the working plane. As I said, very few shades ever need to come down unless it's privacy required. You never want the shades to come down below the working plane because you'll never have a glare problem. The higher you are in a building, the more your clear vision is maintained totally unobstructed all day, every day. This is where things can get very complex. This is a Frank Gehry design. This is the Lou Ruvo Center for Brain Health, which is in the middle of the Las Vegas desert. This is a fundraising space, but the geometry of the building was so astonishingly complicated, it's almost impossible to map the sun's movement around the building. So you can reconfigure how the system responds, and we actually mapped instead the BTU loading per square meter of every piece of glass in the building. So the shades actually respond to a BTU load rather than a solar response. Not many people have designed anything quite that complicated, which is thankful. And here's Aberdeen. When you have a photocell driven solution, a day like this, where you've got low-lying cloud but with a very bright sun behind it, so the whole sky acts as a bit of a light bulb. Recognise that? Never seen it. a lux meter or a photocell won't pick that up. So you can add in, with a scientific solution, then you can add in a brightness override that is looking for something other than pure light to tell you. And what it generally does when you're on a condition like this is it drives all the shades in the building to 50%. Doesn't create a direct glare problem, it just gives you a contrast ratio problem when that's in your peripheral vision. And this is how the advent of mobile phones has been a godsend for this sort of thing. It used to be a very complicated process building a model of a building, certainly in a congested area like London or New York. But mobile phone companies spend billions of dollars mapping central areas to find out where their signals get lost. We can now get access to that and start building in models to see the impact of what glare and what shadow can do. So this is where the hierarchy can move on. Rather than just looking at the sun's position in relation to the building, certainly in London, if you look at London Bridge Place, when the Shard was built and they built London Bridge Place, if we looked at that as a standalone building, you'd have huge elements of sun that you'd be reacting to throughout the morning up to about lunchtime. Because the Shard is there, the vast majority of London Bridge Place is completely in shadow for most of the morning because of how big the Shard is. In fact, there's buildings north of the river that are in shadow because of the Shard when the sun's lower in the sky at the autumn and spring. So we can map how shadow affects it, because as long as that building is standing, we know where the sun is. It doesn't actually matter what the sky conditions are. All the shades can always be up in the areas that are shadowed, because, as I say, as long as that building still remains, you will never have a glare problem. But the other bit that you'll see here doesn't look very orange, but that is orange. That shows first reflection, which is another add-on. Traditionally, you ignore the north facade of a building for shading in any way, shape or form. But if you've got a highly glazed building 50 feet away the other side of the street that is totally curtain wall, you're going to get huge elements of first reflected light coming through the north of your facade because of it. So we can again map where that first reflection drives sunlight into the building, and we can accommodate that within the programming as well and in the response of the shades. Once it gets past first reflection, the sunlight's actually reduced somewhat, which is thankful because the algorithms are so complicated it's hard to try and compensate for 3 or 4 reflections. You can model around a body of water, so if you have an office park like in Reading where you've got lots of low-level buildings around a body of water, if that's a fixed body of water, we can map where the sun would actually bounce up into a building as well. So there's lots of possibilities of how you want to take the response of the building, whether you want to keep it relatively simple to the ultimate response effectively. So these are all the add-ons to what can be done. So it's driven by how much sun you want to allow into any space within the building. You can change it to being a BTU load. You can see the shadows being cast as you go around through the day, and the first reflection that would come across. The gherkin is an incredibly difficult thing to map the first reflection off because it's completely curved. But this allows you to look at exactly what shade position you need to have to maintain the parameters of what the occupants need. And all the time, with the shades in not a fully down position, but as they're coming down, you still maintain that view, you still maintain that connection to the environment around you. That's moving quick, isn't it? This is one of the key points, is that although the vast majority of operations are automated, once people get used to, if they're not having a glare or a heat problem, you tend to ignore what's happening at the curtain wall because it's never causing you an issue. But we go back to the point that as human beings, especially in the UK, not so much in the US, we want to maintain manual control to feel like we can control what we have if we need to. And if you have a meeting space, you may need privacy. You may want to have a secondary blackout cloth coming down so that you can have a presentation room. You may want to just do it for your own sense of well-being, to drive the shades up or down. So we always advocate having either a control by floor or a control by group or a control by person, just to give them that sense of their own control. So we go back to that very initial slide that is thinking about a space where you feel relaxed and you feel rejuvenated and you feel that a sense of well-being with where you are. If we could do everything that I've just spoken about and control that daylight to maximise the amount of natural light you have access to, but without it causing you any glare or heat problems, then all of a sudden that 90% of time that you spend indoors, granted a lot of that is in your home, but we spend large chunks of our day in our working environment in an office. If we could bring that sense of well-being in, then all of a sudden when you start thinking about a space where you feel relaxed and rejuvenated and stimulated, then you start to think more of where you work. And that would be an incredible result for everyone in this room, let alone everyone in the centre of London who's sat in a 1970s concrete building with tiny punched windows. So we go back to it. There's an awful lot of buildings that are, designed for daylight to maximise the use of daylight. Very few are achieving it. What I've just spoken about has been around for quite a long time. The first automated system was installed in 1978, I think, by the owner of Mecco Systems. He did it using conveyor systems and bird boxes that he cut down trying to map when the sun would come in. It's moved on a little bit from there, but it's been around for quite a long time. But the fear of capital cost compared to what it can actually do for the occupants of the space restrict the number of people that will adopt it. But thank you very much, and if anyone's got any questions, feel free.
I just wondered about noise, about the motors. Do they make noise? And have you done some? I presume they've done some measurements to check, what the levels are and whether it's ever been an issue or whether it's too quiet for people to notice.
So the question is about the noise level of motors, whether it's an issue for occupants. Motors now operate at relatively the same decibel level as the fan on the back of your desktop. So they're incredibly quiet, but it's all about the installation. If you secure them up to an open lintel where there's just a sound box above, then it's actually vibration that causes noise, and we've seen some appalling installations where they've not been secured in properly, and that gives you a significant noise issue. But if they're installed correctly, then it wouldn't disturb you. The movement of them wouldn't disturb you any more than the fan on your computer.
Hi, Kieran Davis from Truth Bywaters and Anderson, one of Mike Don's old students. I had a question about the New York Times building, and you mentioned the guy who thought people were going to steal his passwords. Did the post-occupancy evaluation come up with any other anomalies? And I was curious as to the difficulty of commissioning the system and getting it to the point you wanted it.
Okay, so the question was about whether there was any other anomalies with the New York Times with users manually overriding the system, and the difficulty of commissioning the system in the first place to do what we wanted it to do. In terms of anomalies, the vast majority of the movements were meeting rooms where people wanted privacy to do a presentation. They wanted to actually physically draw the shades to allow a level of darkness, which is why there's more. That was the movements, the 1.5% movements coming down. About just under 1% of those were down to having meetings rather than feeling like there was too much sun coming into the space. What we found, we do interviews with the client, the occupants, and the building owner, the developer, before we commission the system, so that we get a very clear picture as to what was required. And there's an element of safety that we put into that. So what happened after the first year, with 2.5% of those movements to bring the shades up to allow more light in, was we moved that comfort line ever so slightly, so that as cloud cleared a space, the shades reacted more quickly and allowed more light to come in. So by the end of the second year, that 5% movement was down closer to 2%. But in terms of commissioning it, the algorithms to drive a system like this are astonishingly complicated, way beyond anything I can wrap my head around. But because they're already there, you base a lot of this on the ASHRAE curve. It's a permanent fixture. So once you've written them, it's not that complicated to start dropping any element into it. So once we know exactly where the building is, the latitude and longitude, and we build a three-dimensional model of the building, we just drop that into the program and then define the parameters of how we want the space to work. So in terms of commissioning, it's effectively plug and play. And any changes can be made by the facilities manager within the building. Anything significant we would do remotely or on site.
Any more?
Paul Littleford, BRE. We've just been doing some research for we're rewriting our publication on control of solar shading, which was first published in 2002.
Mm-hmm.
And as part of that, we did a literature review of case studies like that, and we found that there were quite a number of cases where you had automatic shading which was disabled. And in most cases that didn't have a manual override, and certainly it didn't have the sort of sophisticated algorithm that you're talking about. And I wondered if you wanted to sort of perhaps to say a bit more about what are the sorts of features that ought to go into an automatic control system, especially with regard to manual override.
So the question was really that you've come across several automated solar shading systems that have effectively just been disabled from the building, and the majority of those not having manual control or manual override available to the occupants. We come across it quite a lot. That one of the key things is to explain to the actual occupants of the building what they're getting and what they should expect to receive from the system that's being installed. The majority of the time, if you don't have direct access to the client, which a system this complicated you have to insist on, but slightly less complicated versions, you can effectively plug it into the building management system and let it go. If you haven't explained to anyone sat in the building that this is going to do something for them, the first thing that happens is they realise the blind's going up and down with no input from themselves. They don't know why, they think it's broken. So they start complaining to the manager on the floor, who starts complaining to facilities, who eventually goes, I'll just turn it off then, fine. Because of the lack of manual controls, no one can even sit there and stand at the mullions between the windows or anything else and look at it and go, well, we'll press a few buttons and see if we can drive it. Where they start to have some understanding as to how the system can work. So information is key. Once you have that information from the owners or the key tenants of the building as to what they want to happen, you've got to impart that information on the guys that are actually using it. But the majority, if you go to the US, very few people have manual overrides. The building owner will say, well, if I've paid this much money to start saving some utility cost, I don't want anyone touching it. And that's the American point of view. In the UK, I've not seen a single installation that happened on this scale where we didn't have multiple manual overrides for people to feel like they maintain control. Hope that answers what you're looking for.
Well, just one more last question. If I understood you correctly, so you have a system that takes into account solid geometry and reflections of the obstructions to sort of preset the system, and then you have a roof sensor that sort of overrides as well into the system. My question is, how do you put into the equation the actual layout of the space inside a room, or the area, the dimension of the room that can clearly affect it, have an impact of the blind? And secondly, is the second question is, in your system, how do you normally see the control of a building being operated? Is it individually on a window based, on a floor area, or more or less what's the typical scenario that, because also there is a difference between having a sensor on the roof and when obviously on the facade in terms of...
Yeah. Okay, so I can't keep up. I'll answer the second question first, because that's easier to answer. In terms of what you asked about how you control or how many variants of control you have for any building, you can supply up to 800 or 900 different responses within a building on one backbone. But typically, you would see no more than about 60, because the sun's quite a long way away. So the impact it has in one area, that's actually normally quite a large area of the building at any given moment. So you normally have it split by elevation. You have it split by floor, so that you can just have an entire floor control for maintenance. It then gets broken down into what sort of breakdown in areas. So you'll see on a given floor within the shard, there's only 2 or 3 different elements to what is required on that floor. So every motor can have 8 different commands going to it, telling it to respond to a different stimulus. But normally no more than 60 for an entire building, unless someone wants to get incredibly complex with how they want it to vary depending on the occupancy. And your first question of how we lay out or how we take into account the floor layout of any given part of the building.
Because you don't have any sensor indoors.
No, and it doesn't matter, because what we're looking for is the tenants to tell us what they're using the space for. So if they're having it as a breakout space, we will ask the question as to how close to the curtain wall they will be putting furniture, whether it's soft furnishings or whether it's working desks. From that, we will advise that you wouldn't want the sun to come in more than X into that space. So in terms of what they physically do with the layout, once you get deeper into the space, that doesn't really matter. What our concern is where it starts. So if the layout of the desks is 2 meters into the space, that will dictate to us that we advise no more than 2.5 meters of solar penetration into the room. Whereas if it's just a pass-through area, you could almost have 6 or 7 meters to give them a bit of contrast, so as they're passing through, they get stimulated by more daylight coming in. So you dictate for that room that's the marker in the floor. But if there's a change of use for that particular room, then we can delve into that one particular response and drive it backwards or forwards depending on how the change of space has occurred. So beyond that point, how they've laid the room out, it doesn't have any impact on, once the sun is stopped at a certain level, you're never going to find glare further into the space. So we don't need to map or advise on the layout of the floor plan at all. We just respond to where the closest point is to the window.
Well, thank you very much, Rob, and thank you all for attending our direct group meeting, and hopefully seeing you soon, either paying and then having the refund or just attending, because you're most welcome to our direct group. Thank you.